Hello and welcome to the lecture Neural Network Fundamentals. Today we'll discuss backpropagation. In today's lecture, we'll first introduce feed-forward neural network, then some notations, and mainly we discuss the training procedure of neural network. First, the forward pass, and second, the backward pass as backpropagation. Then we'll give an example of a 4-layer neural network training. Then we discuss computational complexity and space complexity of the backpropagation method. So now we are going to start the training procedure of the neural network. So as we discussed earlier, we see that there is 3 main stages in the multi-layer perception. One is input layer, a set of hidden layers, and one output layer. This input layer is basically acts like a gateway to them. That is, these are inputs are coming. So the main functionality of the input layer, it receives the input features and passes them to the subsequent layers without performing any computation. So it just receives the inputs at the input layer. Next is a set of hidden layers. It may be one, it may be more than one. The main task in the hidden layer is to extract and learn the meaningful patterns from the input data. As I mentioned earlier, the initial hidden layers, which is very close to the input, basically model the very primitive pattern, like for geometrical patterns, some straight lines, slanting lines, and very simple curves. When we go in deeper layer, then these features are adjoining and we get more and more complex features. So early hidden layers basically model the low level features, and we progressively combine this low level feature to capture the higher level and more abstract representation of the features. And that is the one of the major understanding, that this hierarchical learning procedure. So the kind of MLP, mainly when we discuss the deep models, that we understand the deeper the layer, they model more abstract features, more complicated features. Okay. And finally, at the output layer, this produce the final prediction and decision of the network. Okay. So these are the features, what we are things, and then we take the decision. So we apply appropriate activation some function, and that we have seen before, that softmax etc. we use to generate the desired output. So these are the basic setup of a feed-forward neural network. Now let's try to understand the architecture of these layers in notation wise. Layer index I is used and neural index is used as E in a particular layer. Now, what we mean by weight subscript EI and superscript P? It denotes weight on connection from neuron E of P minus 1th layer to neuron I of the Pth layer. This is just a notation. If we remember it, we can understand the mathematical formulations of these layers is there. Now for output neuron I, denoted OY, is computed using a sigmoid or softmax F. The Y of F is equal to sigma, that means summation of e to the power 0 to m, W of weight of EI, H of K, where this WEI is the vector of weights entering output neuron I, and K is the last hidden layer, which is R. So these are the meaning of these notations. Now here you can see here that it is a pth1 layer and there is pth layer, and this is the weight in between. So this is the basically from neuron E of the p minus 1 layer. So this neuron E to the neuron I of pth layer. So that means in between this W, EI and superscript P is basically involved or associated. Now here you can say that M hidden layer with m number of neurons or with odd number of neurons and so on. These are the basic setup of a hypothetical feed-forward neural network. Now the questions are, given an input, how do we compute the output and how do we get the weights? These two questions are very important for training of this neural network. Now, training of the neural network basically two phases. One is forward pass and is backward pass. The backward pass, popularly known as backpropagation, is the fundamental learning algorithm used to train neural networks. It efficiently determines how each weight in the network should be updated to minimize the prediction error. That we will see in the subsequent slide, what the meaning of the sentence. So, the process begins with when neural network makes a prediction. Now, it's a forward direction. In this way, the input comes, then different features are basically extracted at different layers. Ultimately, it get inference or it predicts some output. Now, this prediction is compared with the actual target value. The difference between them is measured using loss function. Now, what actually the backpropagation tells us that how much did each weight contribute to that error. But what we understand here that there may be some difference that predicted output and target or intended output. And if we minimize this error, we can get our intended input output matrix. So the main question, how these weights and biases are determined so that given an input we can get out output. That means we have to minimize the error. To minimize the error, we have to understand, or we have to, depending on the error, how we change or modify the weights and biases. But what we have to understand, how much each weight contributes. That exactly backpropagation tells us. And so once we know that, we can adjust the weights to improve. So this is the more or less the basic story of backpropagation. So as we said, our training process, which is basically backpropagation, has two main phases. One is forward pass and is backward pass. Basically, backward pass is called backpropagation. This input data is passed through the network. This is the forward pass. What we are basically doing, input data is passed to the network. In each hidden layer, as we discussed earlier, the weighted inputs are summed and nonlinear attribution function is applied. That also we know very well. Then the output of one layer becomes the input to the next layer. And in this way, the inputs are propagated in the forward direction. And each layer, the different kinds of features are being extracted. One thing we have to remember that the initial layer extract some primitive feature. But when we go to a deeper layer, these layers are going to model more complicated or abstract feature. And ultimately, final layer or output layer is produce the final prediction. Then, when we predict something, the loss, what is the prediction or predicted output, and what is the targeted output, this difference. The loss is computed using loss functions such as mean square error, cross entropy, so and so. And accordingly, depending on this loss, using backpropagation, we try to modify the weights. So what are the steps of the backpropagation? The error is propagated backward direction from output layer to the input layer. And gradients are calculated using the chain rule at each layer or each subsequent layer in backward direction, that we have to understand. So each weight receives a gradient indicating how much a change in that weight would affect the loss. So these steps we have to understand depth. So first of all, that how a multi-layer perceptron to the forward direction, how output is being computed at y is equal to p of O given I as the input with output. Means predict what is the probability of O given input I. A forward pass or iteration through the network to find output Y for a given I. So this is we already discussed. This is the basic setup of a feed forward network. Input layer. There is the k number of hidden layer, output layer with these neurons. Now this is the more or less kind of pseudo code of this algorithm of the forward pass. For hidden layer E is equal to 1 to k, is equal to 1 to r, let us number of neurons is layer E, n is the number of layer E minus 1. Compute the output of the all neurons of layer E, where y is equal to E I is equal to f of I is equal to E minus 1 W1. And I of E is equal to y, and this E for this to there. And we get the output last prediction of the output. So that is basically by doing in this particular. And that also we understand from 1 to 1 layer. This is we already discussed that from P1th layer to Pth layer, this is basically the associated weight is W EI. So this is way, this is the basic understanding of computed the output of a multi-layer perceptron. Now we take layer by layer. What exactly is happening in different layer? So 4 layers in the network, one input layer, one hidden layer, a second hidden layer, output layer. So this is a hypothetical example, but we take the 4 layers. Okay. So in the input layer, that basically this I is the input, I1, I2, I3, I2, 4 inputs. This is also very hypothetical. Take an example, and these are the inputs are being fed to the action. So no computation is basically done in this layer. It just take the inputs and input to the system or network. So these are the inputs. Now, what happened to the first layer? So in layer 1, this S of I that we already, since it is a 4 number of neurons, so WI1, since it is a 1 layer is B of E, this is the input to this as this base. So E is equal to 1 to 4 number of inputs to the first layer. I is equal to 1 to 2 number of inputs first layer, number of neurons, and B of I is equal to 1 F of H. FH is basically activation function between layers. So it's our very known functions for neural network. Now what happened in the neural network is now is equal to 1 to 2 because now number of inputs become 2 because this is now 2. Inversely it is 4. That's why it was 4 now. E is equal belongs to 1 to 2 number of inputs second layer. I is equal to 1 to number of neurons in second. And is equal to F of H is F of H activation function of the adult. So this is basically the structure. So input layers, neurons copy the inputs to the next layer. So this is the way. Now this is only 2 layers we have given. Now it may be 3, 4 and now at the output layer, what is happening there? This is basically y is equal to f of y is equal to 1 2 because this is 2. So 2 W3 will be Fy is activation function for the layer. So it is basically this way. So this is the somewhat mathematical formulation of the forward pass of the multi-layer perceptron. Now we are going to understand the backward pass. In forward pass, we have seen that how the inputs are propagated in forward direction from input to the output through hidden layers to get some output. This output is predicted and we get a target output in supervised mode and we can get the loss. Now in backward pass, this backpropagation algorithm essentially minimize this loss. The basic difference between the actual output, that means intended output, and the predicted output. So backpropagation minimizes this loss by updating the network's weights and biases using an optimization algorithm such as gradient descent. So this is the basic way of backpropagation for training this neural net. So one thing we understand, the forward propagation in this direction, input to output, but backpropagation in the reverse direction, output to output. So why this error gradient? Now this error gradient help of learning rate indicates how much each parameter should be changed and in which direction to reduce the loss in a particular epoch on a particular iteration. So this error gradient, now will come the, what is learning rate later. This error gradient is basically to help or to make us understand that how much these weights and bias are modified so that we can get, given an input, we can get intended or targeted output. Now, what backpropagation basically do, or what is happening in backpropagation? These gradients are propagated from output layer back to the input layer. and hence the name backpropagation. And how actually it propagated, that we'll see, that we use the chain rule. So the gradients are computed directly at the output layer. So gradient is basically error gradient computed here, and then propagated through these hidden layers to the initial hidden layers towards the input layer through the hidden layer using this chain rules of calculus. So we'll see in subsequent slide how chain rules are used to find out the error gradient at different hidden layer, so that weights and biases can be modified accordingly. Now here show that weight updation, how weight updation is done in backward detection using chain. Now here this is the output layer, and what actually we are telling is, what is it? This is the difference, that D, let's say D is your actual is the predicted output and D is the actual, and we get this E here. Okay? Now this thing we can calculate here, that del of EY is del of WY. Now this WY is what? The weights associated in the output layer. These are WY. Okay? So here these weight gradients are basically calculated at the output layer. Now when we go to the first layer, let's say HK layer, how it is being done? Using this chain rule. That's del of EY, because it is del of EY, that this. But now what we require? This del of WHK, that is this WHK in this layer, because, and what we get, W of EY, the del of WHK is in W of Y and D of E of E of Y and del of W. So in this way, so from when this layer to next HK minus 1 layer, we use this similar thing, that this we can use the chain. That's that this we have W of HK, now by W of HK minus 1, W of Y HK and D of UI. So ultimately this is basically we know, and from this, using the chain rule, we can go next by this initial layers. Ultimately this is the chain. So one thing, it is very important. Now when we get know that at what in this layers it means, what is important, that these notations or these mathematical expressions are just for explaining, but what thing we have to understand, that each layer, when we get know the error gradient, we change these weights at this layer from iteration to iteration. So that is basically that thing. WEIK minus 1 small, EIK minus 150 minus, this is learning rate, W of EY, W of HK minus 1, because this is that particular layer. So you have to know this error gradient at each hidden layer, and we multiply it with learning rate and subtract from this the previous iteration this weight to get the new weight value. So by iteration, by 2 iteration, we get the different value, and these basically these weights, it is by some our optimization algorithm we can ensure that these W's are close to that, the intended value of W's is weights and biases, so that we can get for a given input the target output or very close to it. So this is as a whole the basic understand or kind of visualization of backpropagation algorithm. Now in backpropagation algorithm, we first try to understand. We have used the sigmoidal nonlinearity, and this is basically denoted by out of this 1 by 1 plus e to the power minus s. If we take the derivative of this, that is rs is 1 minus rs. So that is the first thing that we have to understand. Now again we some notation. Let we have a k layer multi-layer perceptron. It consists of one input layer and k hidden layers, as we have discussed earlier. Now the eth node of the kth layer neuron is denoted by IEK, which is the output of the eth neuron k. And so I of k plus 1 is basically this sigmoidal nonlinearity over this series summation 0 to k. W of ei, this is the corresponding weights, and the ik, where mk is the number of nodes. So this is the basic notation of this. Now if we calculate the error, then E is basically half of mk, ik, this is our predicted output and this is the actual output. Take the difference, we do the square and we sum it up over number of neurons at the basic output layer and take some normalization. So this is the output layer, what is E. Now if we take the gradient of this error with respect to the weights at the output layer, we can get this. If we these two come here and others is not d of eik become 0, so this comes. And if we put these things, d of this I of k, that what we have find here, I of k, so that definitely it is k plus 1, so it is a k, so it is k minus 1, so it will basically sum it up is equal to 0 vi. After some algebraic manipulation, we get it I of k 1 minus I of k e by k minus 1. So this is the some mathematical derivation of this particular gradient at the output level with respect to this weight at the output level. Now at output layer, what we get if we put it here, if we put it this value in here, so actually this is our error gradient. We put these values here and these values here, so this becomes, now here w of e I k, this become I of k minus d of I dk into I of ik, so 1 minus I of ik. So at the output layer, this is the error gradient. So if we use it in weight updation at the output layer, it is basically this wei equal t plus 1 of wei equal to t minus this error gradient, learning rate, and this error gradient. And we put this error gradient here, so it becomes this. Now for just simplicity, we let this delta ik is this part within this rectangular box, so that it is becoming now this weit plus 1 at the output layer. So this is the feed forward backpropagation algorithm. So backpropagation for the feed forward neighborhood. Now if we sum it up in basically summarize this in algorithmic form, that we initialize weik feed forward feed training samples. Now feed forward network for k is equal to k plus 1 is equal to ik plus 1. We can use this as forward formula. And then we go to the back propagation. At the output layer, del of I is equal to k I of I k d of I. And that's what we have. But for not output layers, it is becoming this. We have not shown the detailed mathematical formulation for that, but it is basically coming from our chain rule that we have discussed earlier. Okay. Now we are update weight in this formula and we repeat step 5. So this is our back propagation as a whole. Now example of this back propagation algorithm, that is loss is d minus d here, and d is the target value, d is the predicted value, and gradient loss is output layer with respect to the output, d of e of y of d of, and these are the basic chain rule we have used, and we have do this particular loss and how the loss is basically propagated through the first and the last hidden layer next to and so on into the input layer. Now what is the computational complexity of the backpropagation? The computational cost of the backpropagation is basically dominated by the matrix multiplication operation carried out during the forward and backward process. As the number of these operations scales with the total number of trainable parameters, the computational complexity is given by W, where W denotes the total number of trainable parameters, weights and biases. L is the number of layers in the network, and L represents the number of nodes. So this is basically W of is equal to I L is equal to 1 to capital L, N of L minus. Now computational complexity in forward pass is big O of W, which in the backward pass backpropagation consider gradients with respect to the weights and gradients and with respect to the activation for the order of W. So the computational complexity O of W. So for both sides B, the complexity becomes B dot W. Now there is another thing, there is a space complexity of the back. The space complexity backpropagation determined by the memory required for the store model vectors, intermediate activations, and gradient. So there is the 4 basic important parameters, that is storing model parameters, the weights and biases of the network, the stored throughout the train. W is the total number of trainable plus that required memories about that. Storing immediate activation, the output activation of each layer are cached during the forward pass of use in computation. So the memory required goes linearly, number of layers and movements. How about storing gradients? The provision stores the gradient corresponding to trainable parameters. Since there is one gradient per word bias, memory required is big of W. Overall space complexity is big of W with the additional memory required storing the immediate activation. So some checkpointing is optimization step. Standard implementation requires often space for store activation. Checkpointing or selective recomputation trades computation time for reduced memory usage. So standard approach is big often space store all intermediate activation during the forward pass. Fast computation but high memory usage. Recomputation approach big of one space more big often square time. We compute the activation during the backward pass instead of storing them, minimize the memory usage but increase the computation time. And checkpointing the store only the selected activation and recompute the rest as needed, balances memory and computation and space complexity between big O and N. So this is the output complexity. So in this particular lecture, we basically try to understand what do you mean by feed-forward neural network, what are the basic notation used in this lecture, then 2 basic passes of training this neural network, forward pass and backward pass, then training neural network, 4 layers of neural network, computational complexity and space complexity. In the next lecture, we'll basically optimizing supervised model. Basically, we study about overfitting. Thank you very much.